Hello, Chemistry 12 students. This is Mr. Chan. Now, last day, remember we talked about the Ka value and how that applies to weak acids, okay? And remember we went over the chart here where we talked about Ka values and how Ka values only apply for weak acids. So what about weak bases? What about all the chemicals down the right-hand side? And that's what I want to focus on today, just for you to be aware of, okay? So for a weak base, okay, remember, it's anything found on the right-hand side at equilibrium on the table. So let's say we have NH3 plus H2O gives you NH4 plus OH minus 1. Because NH3 is a weak base, what happens is that it's at equilibrium. And so we have a Kb expression where we have the products over the reactants. Now, for Kb, it deals with weak bases. And just like Ka, the Kb increases, the concentration of OH minus 1 increases, therefore the stronger the base. So just like Ka, where you have the larger Ka, the more dissociation, the stronger the acid. With Kb, again, larger the Kb, the stronger the base, the more dissociation, the stronger the base. Now, one thing I wanted to note here is NH3, when you take a look, you might say, Mr. Chan, we see NH3 here. So let's look at the acid-base chart. So if I scroll down, what you will notice is that there's an NH3 right here and an NH3 right here. Mr. Chan, isn't NH3 an acid? Why did you consider it a weak base? In this case, NH3 technically is an extremely weak acid because it has a hydrogen it can donate based upon the Lewis theory of acid bases. But what we want to do is we want to focus solely on the fact that NH3 tends to be a stronger base. It will tend to want to accept a proton rather than to give up a proton here. So that's why you find it on both sides. NH3 does have a proton it can give, but it tends to act more as a base by accepting a proton. Now, when you take a look here, notice, even though we have NH3 is a weak base, there's no Kb value. All you do is you have Ka. So where is the Kb values? Is it because people are just lazy? They didn't want to put another column for Kb? So why is there no Kb values down the right-hand side of your chart? And it all has to do with there is a special relationship between Ka and Kb. So if we look at Ka and Kb, where is it? Here we go. There is a relationship between Ka and Kb. For conjugate acid-base pairs, there's a specific relationship between Ka and Kb. So let's say, for example, we have H2CO3 and HCO3 minus 1. They are conjugate pairs because of the fact that they differ by one proton. The acid is H2CO3. The conjugate base is HCO3 minus 1. Now, H2CO3, is found on the left-hand side of the table, so it tends to be a weak acid, as illustrated by the equation in blue. HCO3 minus 1 tends to be a base, as illustrated by the equation highlighted in orange. They each have their own equilibrium expressions. You have Ka and you have Kb. Now, so again, if we were to look at the acid-base chart, I'm focusing solely right here on H2CO3 and HCO3 minus 1. Some of you might say, well, Mr. Chan, isn't there HCO3 minus 1? But then the conjugate base would be CO3 minus 2. Okay, so please be aware of that. You're looking at the acid and its conjugate base. All right. Now, so when we look at that, what happens? What's the significance of that? Here we go. So what happens? I don't like it when that happens. So what happens is if we combine the Ka and Kb values by multiplying them together, what happens is if we combine the two expressions together and we multiply them, what we can do is we can cancel out like terms as what is highlighted in red. And after we cancel out the like terms, we notice that we're left over with H30 plus times OH minus 1. And you recall that is the equation for Kw. So when you multiply the Ka value times Kb value for conjugate pairs, you get Kw. Okay? Now, example would be like this. So if you were to ask to calculate the Kb for F minus 1, so the first question would be, what's the conjugate acid? It is HF. Remember, conjugate acid means that it differs by a proton. That's what conjugate means. And acid, what you do is you add on an extra proton. So the Ka for HF is 3.5 times 10 to the negative 4. Where did I get that value from? Is if you look at the chart, okay, so HF, if we scroll down, scroll up, we have HF, we have 3.5 times 10 to the negative 4 on our acid base charts. And then we just, because it's a conjugate pair, then what we do is we just plug in Kb is equal to Kw over Ka of HF, which is the conjugate pairs. And what we do is we do our calculations, and we get an answer of 2.9 times 10 to the negative 11. And so this is why you don't need a separate column for Kb values, because if you know the Ka, it's very easy to calculate the Kb for the conjugate base. All right, ladies and gentlemen, that's a very short lesson on Kb. All right, now you might say, well, Mr. Chan, what about the, if we were to do any of the calculations like Ka? Because it's a weak acid, you do the exact same thing where it is you figure out the ice tables and then you plug in the information. All right, ladies and gentlemen, thank you. Have a good day. Bye-bye.